Okay, so for today, we're gonna talk about tolerance and alpha fitting. But before that, let's watch a video first. And the video also has been explained in the has been uploaded in the EduNext. So let me check the courses. Okay. Okay, so so today for this the third week, we have wait wait a second, still loading in here. Or maybe let me change the internet Wi-Fi. Okay, so here I have uploaded. There are three videos about fit and tolerance. Okay, so basically all of the video is quite similar, but maybe we can watch for different two videos to have an idea more about limits and fits that this is would be the introduction for our discussion for today. Okay, so maybe let's I think it's good if we can watch this video first. Okay, and then let's have a look.
The vast majority of engineered products have multiple components that need to fit together. Sometimes you need components to slip together easily, while other times you need components to press together and not come apart. There's a systematic way to design parts so that they fit together exactly the way you want on the first try every time, and in this video we're going to show you how. The engineering term for this consideration is fits and tolerances. Let's define these terms. Most of the time, especially in CAD, we just type a single exact number into the computer for our dimensions. That's called a nominal dimension. But when it comes time to actually make that part, we won't be able to manufacture the features to exactly those dimensions. Each feature might be slightly larger or slightly smaller than the number we originally typed into the computer. So we need to specify a tolerance, which tells the person manufacturing the part how much of a variation from our nominal dimension is acceptable.
Different manufacturing processes are capable of different tolerances. This chart shows a variety of different manufacturing processes, as well as a general idea of the tolerance that can be expected. It's important to remember that tolerance capability corresponds to a large production run, where factors like tool and machine wear, deflection, sharpening, and the natural variation of different processes apply. A very common mistake that new engineers make is selecting tolerances that are far tighter than necessary. As the tolerances become tighter, the cost to manufacture the part grows exponentially.
So how tight of a tolerance do you need? Tolerances typically come into play when designing fits. In some cases, you might want components to slip together easily, but not have a lot of perceptible play. In other cases, lots of relative movement is okay. You might even need to have two components come together permanently and not come apart. These different cases are called fits. Machinery's Handbook is the go-to reference for designing fits. Fits have a particular naming convention of a two-letter abbreviation followed by a number. The letters denote the type of fit, and the number corresponds to the tolerance class of the fit, with larger numbers representing looser tolerances. This graph shows all the standard ASME fits. The solid bars represent the acceptable tolerance of the shaft, while the hashed bars represent the acceptable tolerance of the hole. The scale of this graph corresponds to a 1-inch nominal shaft. This video deals primarily with ASME fits in the inch system, but there's a similar convention for metric. The naming convention is different, but the general concept is the same. For more information, you can reference Machinery's Handbook or ISO 286-2. Since the chart only applies for a 1-inch basic size, we need to use tables to design for other sizes. The process is easy, and we'll show you how with an example. The first fit we'll show you is the loosest. This is an LC11, and you can see there's lots of clearance. To design this fit, first we'll look up the LC11 column, then we'll find the row that corresponds to our basic size. At the intersection of the size and fit, we have a tolerance range for both the shaft and hole. Notice that these numbers are in thousandths of an inch. You'll use the same procedure to design all the other fits that we'll talk about.
These tolerances are extremely loose, so drilling the hole with a regular drill is sufficient. Hitting the shaft tolerance on the lathe is also no problem, and other processes like forming and extrusion will probably hit it as well.
This fit is used where you don't need accurate alignment of the mating features. The clearance around a bolt is a good example of this, since you typically don't use a bolt for precision alignment. This is a slightly tighter locational fit, LC9. It provides less clearance and has a tighter tolerance than LC11.
This is probably about the tightest hole tolerance that can be drilled, but turning shouldn't be a problem for the shaft tolerance.
You can see that the LC9 fit is a bit tighter than the LC11, but both can still be easily achieved with standard equipment and tooling. The next category of fits is called running fits. A running fit is typically used when you need two parts to mate together freely, or that's to say without any force, but you need some degree of precision in their alignment.
We ream this RC6 hole, but you can probably achieve this tolerance on a CNC mill if you compensate for tool diameter in the control. A drill is not likely to hit this tolerance every time. Depending on the size, this is probably about the tightest shaft tolerance that you can expect to hit consistently by turning.
This is the fit to use when you need two parts to align to each other, but some clearance is acceptable. This is the tightest fit that can be readily achieved with normal manufacturing processes and without undue effort. For the rest of the fits in this video, we're going to have to work a bit to hit the tolerances, and you're going to want to be absolutely sure you need this in your design because you'll be paying for that care and attention. This is an Rc3 fit, which is a tighter running fit. In general, this fit is going to have almost no perceptible play.
This hole will need to be reamed or bored. You can also interpolate it on a CNC mill, but you will probably have to update the wear offsets throughout the production run to compensate for tool wear, and you'll need to be sure that tool deflection isn't causing the feature to taper with depth. A rigid lathe setup might be able to hit this shaft tolerance consistently, but as with the hole, you'll need to perform regular inspections throughout and adjust the wear offsets. A lot of parts, especially flexible ones or those made of tough materials, will require grinding.
Here's a comparison of the two running fits. The Rc6 has some perceptible play, while the Rc3 has almost none. Rc3 and tighter will precisely align components, but can still be assembled easily by hand. This next type of fit is called a transition fit, and it requires a slight amount of force to assemble and disassemble. However, there's absolutely no play once the pieces are assembled. The tolerance required for the LT3 fit are about the same as the RC3, but the range of the shaft has been shifted so that there's a slight amount of interference. If we add a bit more interference, we create what's called a force fit or a press fit. These fits usually require a press to assemble and are intended to be a permanent connection. We hope you enjoyed this video. If you have other topics in mechanical design engineering that you'd like to learn about, leave a comment and let us know. We're coming out with new videos soon, so please be sure to subscribe. Thanks!
Okay, I know it's still a bit confused, yeah. You would be confused about that one, but that's all right because this is what our this is what we're gonna talk for today. Okay, so now let me share the screen from the other side. Okay, so the video you're just watching is actually talking about fit, yeah, or suayan in Indonesia, yes, fit. So fit, or because in many machineries, in many parts of components, or yeah, between, for example, between doors or something, there would be always a pairs between a hole and a shaft. Okay, and then whether it should be loose, whether it should be tight, and then there should be some measurement for that one. So this chapter tells you about, we call it linear tolerance, toleransi linear, and also fitting or suayan. Okay, so the specific learning outcome for today is actually to understand the concept of tolerance and its relation to engineering design. Okay, so you may find that several type of suite or fittings, like in the videos, there are the one that is looks really loose, the one that would be very tight, yeah, or maybe if you have Lego toys, and then you know that it is not loose, but it is quite fit, for example. Give me 1 second, I'll try to find toys or something, yes, so I can give you some more Okay, so yeah, another example. For example, I have this Lego toys. Yeah, the Lego toys. So if you think about it, there are the shelf. The shelf would looks like those little tiny points there, and this is another part. And then if I can press this down really easy, because it is quite tight. It's not tight sweet, yeah, but it's called running sweet, which is you can put it there, and then you can open it easy like that. Okay, so I think the Lego Lego manufacturers have built a very excellent system in the world how to make Lego. So even if your father or mother has these Legos from around 80s or 90s, and then you now playing with this one, this would be also sweet with this maybe new Lego. Okay, so from 20 years or from 10 years or 5 years, all the fitting is just everything just fine. Okay, or even in different parts, I can easily open it and then maybe close it. Okay, so this is one part, an example in Lego. Yeah, just an example. Okay, so now what is the what is the corresponding this one, and also the color. So when they want to make the component or the parts, first one they have to make the drawing first. Okay, in this drawing, in this engineering drawing, we have to make a component or work piece, ya, benda kerja, or the piece, and then after that we have to make it we have to machine it in the workshop. Okay, so the one that they make it with the turning and so on, it is called the one in mechanical engineering, or we call it workshop. Okay, in Bandung, for example, Polytechnic Swiss, ya, or Polytechnic Polban or Polman, ya, Polytechnic Manufaktur in Dago, Bandung, or maybe Polytechnic Negeri Bandung, or they the vocation specialized to do this on the on the workshop. Okay, but for us as engineer, we usually need to design those drawings. Okay, so the deviation of the design, even we make a very good drawing, but when we're manufacturing that, there are some deviation. Okay, for example, the shape and the size of a workpiece, the method of manufacturing, the tools that's used, and also the material. Okay, if the for example, I have a 3D printing at home, and then the deviation is really 0.02 millimeters, so it's very low. Okay, but if we ask for example the what's it called, tukang-tukang, ya, tukang bangunan, try to make some pieces or something, I think they will have a deviation around 1 milli or 2 millimeters, something like that. Okay, so in order that we can get the desired workpiece size, the material that we want, or the specimen that we want, the component that we want, and it also make it easy for the workshop person to do that, we have to include in the drawing the tolerance. Okay, so the tolerance means the upper and the lower deviation limit. Okay, so we have to write the nominal size, so how much is the length, okay, the length of this piece, for example. Okay, this should be exactly 100 millimeter, okay, for example, yeah. Okay, and then after that we have to add the enlarge the upper and also the lower deviation limit. Okay, so the tolerance is actually the difference between the enlarged deviation limit and the deviation limit that is smaller than nominal size. Okay, okay, so this one also we have a video on bolt and nut, but actually this is about manufacturing process, so I think I can skip that. Okay, so linear fit and tolerance, that would be good and cater for imperfect manufacturing process, and then so we can produce and then have the size of the components within functional limit, and then we have variation in value on of the dimension, and this one also we will control the manufacturing process. Yeah, in the any manufacturing process we have to process about 100,000 of parts every day. Okay, for example, in the plant that manufacture bolt or nut, okay, they should make a lot of things. Yeah, there would be a lot of things, maybe 100,000 parts maybe, and then we also have to control the variation between mating part, because for example, okay, this one I have another toy as well, what is called, I think Bionicles, yeah, and then in the Bionicles, I forgot where is it, but for example, there are some very small part, and it should be put it there, so or maybe pick another one. Yeah, so this is actually we call it the mating part, ya, bagian-bagian yang berpasangan. So if we can have a very good control of the variation of mating parts, that means that we can always we can always mate them, bisa dipasangkan with the part that should be required to. Okay, so and also it allows the interchange of parts. Okay, Lego is a good example, because Legos from 20 years ago, from 10 years ago, and now it can be fit perfectly, because they have a very small linear fit and tolerance. Okay, so the concept of tolerance. Oh, and then before we continue, I also asked the other lecturers, and they said that for the exam it's actually a closed book, so that means you have to remember all of this. Yeah, so you have to understand and remember all of this. So I think while you listening to my lecture, you need to also to maybe print it out, this as handout, or put it in your laptop and then maybe read it again and again until you understand and remember. I think that is would be good for you to prepare the exam. Okay, let's continue. So the concept of tolerance is needed to facilitate manufacturing activities and also lower manufacturing costs. So it would be very difficult if when we're making a product, the size or the dimension must be exactly similar to design. Okay, and then the tolerance will allow interchange between products and component when the product is assembled or replaced. And then so the tolerance is allowed depending on the function and quality. Okay, that would be good. And then so the length of study table and the length of ATM card has of course very different tolerance range. When the ATM card is larger than the machine slot, of course the card is not cannot enter, so the machine slot should be a little bit larger than the ATM card so they can enter. Okay, and then an example function is this one. Yeah, so the precision or the very good tolerance, it determines the cost of the product. Okay, it determines the cost of premium product or the second class product or the third class program or KW1, KW2, KW3 products. Okay, so for example, the Toyota and Mercy, they have the same sedan but different price. Okay, and then the factor of course is the tolerance of different parts that the price becomes different. Okay, another example again about the toys, about the Legos. For example, between the difference between the quality is the manufacturing part. For example, I bought one from Lego, which is a very famous for making building blocks like this. And then in the past I also bought from Hasbro. Yeah, if you know Hasbro, they're also making toys, but they're their main business is not making building blocks like this, like Lego. So that at that time I was in Australia, and then my son was about 4 years old. So okay, let's buy this. Yeah, like the toys or like building block as well from a Hasbro. It's about Transformer or something. And then when we make it, we found it very very hard. Sometimes there are some part that very it's not really adjustable. Sometimes there's would be such a little gap, or sometimes it's very hard to be removed, something like that with that Hasbro, yeah, with the other type of toy. So that makes us not enjoyable at all for making toys. Okay, when building blocks and making the transformer, Legos or something. So I think I can understand. So maybe different price or different quality, that would be resulted in different different quality. Yeah, that one. Okay, and then of course based on the tolerance. Okay, so the tolerance it depends on the function of workpiece, benda kerja, the pairs of workpiece between those pairs, and also the deviation of the form permitted. Okay, so I think for you just need to be able to read and to understand which part is with. Yeah, of course, for mechanical engineers or our friends in polytechnic or vocation, they need to know how to design as well about all the tolerance. Okay, so for example, this one, the tolerance is written with the front size of a number smaller than the standard for nominal size. Okay, the font size. Okay, and then so for example, this number, this is 25, and then you have to check is it 25 millimeters or 25 inch. I don't know, I think it's millimeters. And then you have to see the upper one is the higher tolerance. Okay, and the lower one is the lower one is the lower tolerance. So that means we can actually make this. It's allowable to make the part with that length with tolerance of 25.2 and then maybe 24.9, yeah, which is from 24.5 minus 0.1. Okay, so here the deviation is written after the nominal size. Penyimpangan membesar ditulis di atas. So the upper deviation is we put it up there, okay, and then penyimpangan mengecil ditulis ke bawah atau sejajar dengan ukuran nominal, which is the lower part, the lower deviation is put inside over here. Give me 1 second first. Need to check. Okay, right, okay, and then for some for example the upper one, ukuran luar, for example between the porous hole, the hole as shaft and the hole, ukuran dari lubang, ya. So it's actually it's still written still in Indonesian, but in English it's actually poros, we call it shaft. Wait. So this is called shaft, and this one is called hole. Okay, so for the part like shaft and hole, we write it just individually like this. And then if we have deviation 0, we also need to put it 0. So for example, this is the number 20, so 20 millimeters, but with the upper deviation is 0.35 is allowable, and the lower one is 0. So during the manufacturing, the workshop person, they can make the specimen with length maybe 20.30 is okay, 20.20 is okay, 20.1 is okay, but for example 19.4, for example, it's not allowable because the minimum, the lower deviation is 0. Okay, and then the deviation are written in the same decimal, except for deviation there are 0. So for example, this is equal to 18 millimeter for the nominal size, and the upper one is 0.25, and then the lower one is minus 0.1. So the allowable manufacturing, when we measure it, is minus 0.1. Okay, and if it is we use the same deviation, we should use a plus minus, so that should be, we have to write plus minus in here. Okay, so that is some rules for deviation. So this one is the tolerance on the combined object. For example, we have a part over here, and then okay, and then this is actually like a hole, okay, and then we put some porous or a shaft, yeah. So we have the over here we have the hole, and this is also the shaft. Okay, so here if we have the loose fitting, suaian yang longgar, yeah, of course we know that the shaft should be smaller compared to the hole, right? So if you look at here, so the hole, let's write it. So this is shaft. So this is hole and this is shaft. So you can see here that the shaft or porous, it should be 30, but both the tolerance is minus. So 29.9 and the lower one 29.8. Okay, from that one. But the hole should be larger than the shaft, which is at 30.02 for the upper deviation and 30.0. Okay, so the machine should be able to manufacture those parts. Okay, so the size of the hole is always placed above the line of designation of the size, and the shaft of shaft placed underneath. Okay, and the designation of the size is written whole shaft or position number respectively, and we can write that one there ya. Untuk bagian silinder dan bujur sangkar dicantumkan simbol yang sesuai. So we can also write in this one. So this part number 1, which is the hole, is this part. This is the numbers, and this is the part number 2. And then from the graph we can know that the part number 2 is actually the shaft, which is 30, and then both of the linear tolerance is minus yeah, minus 0.1 and minus 0.2. Okay, and then again in the angle, the tolerance should be written in degree, minutes, and second, like in previous weeks, and the designation of angle size should be similar with the designation of length. Okay, so this is a very long one. So before we continue, I think let's watch another video. Again, still the same with about the fitting, but with different perspective. Yeah, at least you can have more ideas about this one. Okay, so let's open it. Where is the share screen? Okay, and then let's watch the first video. So it's about 10 minutes. So let's watch this one, and then if you have any question, and then let's discuss them before we continue. Okay.
I've wanted to make this video for a while. It's on something I've found very useful over the years, and I hope you will too. The ISO system of limits and fits.
Okay, but before we finish, so this is called the parts. Okay, so this is called the parts, and then this one is the cutting, yeah, the cutter and the machine. So to make parts, we have to make this circling like this, mutar ya, kita rotating, and then after that we can cut this one a little bit with this very sharp edges, maybe made from metal, sometimes made from diamond. So we can make a hole in here, we can make ukiran ya, gambar, or we can make or we can lower the diameter. If we make turning over here, can be diameter. So this is actually a very common in mechanical engineering or in the workshop, and this is how they want to make the parts from the drawing that we make. Okay, so let's have a look. Where is it?
Contrary to most of the other videos on the topic, I'll be presenting this with a working microphone. If you've seen as many videos online as I have about this, you'll get that joke. Before I get too far into this, I want to say that this is my understanding of the ISO limits and fit system, and I did do my due diligence to make sure it was correct, but if I make a mistake, please let me know in the comments so I can either add edits to the description, or if I'm way off base, remake the video. So starting off, any dimension in existence has some tolerance to it. The tolerance specifies how much higher or lower a dimension can be from nominal and still be acceptable. The space between the upper and lower limit is often called the tolerant zone. Think about it like football uprights. Each upright represents a limit, upper or lower. To score a field goal, we kick the ball towards the center, but no matter how the ball flies, as long as it ends up between the uprights, it's acceptable, and our parents will still love us. Before we get any further, I should mention that I'll be talking about shafts and pins fitting in holes, but per ISO 286, this system can be used for internal and external features of size. You'll sometimes see it used for keys fitting in keyways, for example. How things fit together is determined by how much free space there is between the two parts. If there's lots, there will be lots of space for the parts to move. If there's only a little, there will be a lot less space. Finally, if there's no space, the part won't be able to move. In this video, I'll show the hole tolerant zone is red and the shaft tolerant zone is green. This means that without measuring, the actual outer diameter of the shaft will end up somewhere in the green zone, and the actual diameter of the hole will end up somewhere in the red zone. A pin can fit into a hole one of three different ways: clearance, transition, and interference. A clearance fit means that there will always be space between the two parts, no matter how the tolerances turn out. Transition fit means there's sometimes space between the parts and sometimes there isn't, but it's usually pretty close. Interference fits never have space between the parts, and one part always has to be forced into the other. It turns out these categories can actually be quite broad. For example, a 9mm pin fitting into a 10mm hole is a clearance fit, but it would be extremely loose. A 9.98mm pin in a 10mm hole is also a clearance fit, but it's much tighter. The former might be good just to make sure two parts don't hit each other, and the latter might be good for making sure the pin stays approximately in the same position relative to the hole. Different fits, as well as their descriptions, can be found by looking up preferred fits and tolerances in the machiner's handbook. There's a preferred fit for most situations, and this is a really good starting point. Also, check out the YouTube video by Tarka on the ANSI system of fits and tolerances. The designations are different, but the concepts and considerations are the same. So if we want a dowel pin to fit loosely in a hole, we measure it, we ream the hole to have a little extra space in it, and we put it in. The problem arises when you have a bag of 100 dowel pins and you have to ream 100 holes. Dowel pins have a tolerance on them, and their sizes will always vary a bit. Your reamer will also cut slightly different sized holes, depending on your work holding, wear in the reamer, and the cutting parameters, all of which can change while reaming your 100 holes. Because you bought the dowel pins and have no control over their tolerance, this is called a shaft basis fit. So the challenge is now to decide what size reamer to use to make sure that all the dowel pins fit properly. If you know the tolerance range you can expect from your reamer, and you know the tolerances of the dowel pins, you can choose a reamer size where the smallest hole the reamer can cut still has space for the largest dowel pin. This is called the allowance, and is typically something you choose. You're allowing, say, 25 microns of space between the largest dowel pin and the smallest reamed hole. Because there will be other smaller pins and your reamer will sometimes cut larger holes, you may also find yourself cutting the largest possible hole for the smallest possible pin. The extra space on top of the allowance is called the clearance. If the clearance is too large, the fit might not work. The only way to change the clearance without changing the allowance is to tighten up your tolerance zones, either by changing your manufacturing methods or buying tighter tolerance pins. Conveying tolerance zones can be a bit annoying. Say you own a factory that makes dowel pins. You want to be able to tell customers what the tolerance zone is on each size of dowel pin, but it would be cumbersome to have to create engineering drawings for each size. So instead, you can just say the tolerance will always be a bit over the specified dimension, where a bit over scales roughly proportionally to the target size. We could say that all the pins will be between 0.1 and 0.3% larger than the nominal dimension. The problem is we don't want people to have to constantly calculate what these percentages are. The system we use instead is called the ISO 286-2 standard. ISO 286-2 uses numbers and letters to convey tolerance zones, things like M6 and H7. The number, also known as the international tolerance grade, roughly indicates how large the tolerance zone is, and the letter indicates roughly where it is. The letter H always means that the specified tolerance zone includes the nominal size as one of the limits, and it diverges into the material. For holes, H means the smallest the hole can be is the nominal size, but it's allowed to be larger. For shafts, H means the largest a shaft can be is the nominal size, and it can only be smaller. The H tolerance zone is important because it's taken as the middle. Shafts or pins with tolerance zones before H in the alphabet will never be the nominal size. Holes will always be larger and shafts will always be smaller. After H, there are a few tolerance zones, such as J and JS, where the shaft can be larger or smaller, but as you go further through the alphabet, the shafts will get larger and larger and the holes will get smaller and smaller. Holes always get an uppercase letter and shafts always get a lowercase letter. Okay, so now we have a naming scheme for tolerance zones. For a given fit, we will usually have one component driving the other one's required tolerance zone. In this example, where we bought the dowel pins, we have no input on their tolerance, so it was a shaft basis fit. If we're designing a shaft that has to fit in a purchased bushing, We can't control the tolerance of the bushing, so we have a hole basis fit. Shaft or hole basis fits often use an H-tolerant zone, respectively, since the H-tolerant zone contains the nominal size as one of the limits. If we're lucky enough to be designing both parts, we do have some discretion, but you would normally base your fit on whatever side of the fit is harder to change. The preference tends to be designing for a hole basis fit, as in general there tend to be more options for precisely reducing the diameter of a shaft than precisely expanding a hole. So what does a fit look like in the ISO system? It's simply the two tolerant zones specified next to each other. An H7G6 fit means, for example, the hole has an H7 tolerance and the shaft has a G6 tolerance. I've cut some holes in this piece of aluminum to show some examples of different fits. This is an undersized H6 tolerance dowel pin. The E7H6 and F7H6 are reasonably loose clearance holes. You can rattle the 12.7mm H6 dowels around a little bit, and they basically drop right through. The H7H6 and G7H6 are much closer fits, and could perhaps be used to locate parts while remaining removable. The J7H6 is a transition fit that, as you can see, ended up being on the light interference side, but a rubber mallet would work to tap the pin in for a semi-permanent joint. Finally, the P7H7 is an interference fit and would probably require a hydraulic press, or at least a beefy arbor press to install. This might be a good time to point out that, contrary to my labels in my past example, individual holes and shafts can't be called JF7 or H7. The JS7 refers to the tolerant zone that the hole falls in. A hole that is 10.001 millimeters is in the JS7 tolerant zone, but it's also in the H6, H5, and JS5 tolerant zones. You have to remember that we can't measure the hole until after it's cut, and we have to specify the acceptable tolerant zone before it's cut. The fits also have some range to them. For example, these...
Okay, I think we can stop here, and then I will explain to you in the few slides. So later on you can watch the video again to get some more description about the fitting and also all the codes. Yeah, so the codes are actually based on the ISO system. Okay. All right, let me stop here, and then I would like to invite you if you have any questions. Please, anyone? Or maybe still try to digesting. All right.
Actually, Miss, may I ask something?
Yeah, you can.
I'm still not entirely clear. What's the difference between the uppercase and the lowercase letters?
Right. That's a good question. So the upper one and the upper and the lower one is actually the tolerancy. Yeah, the tolerance when you make something. Okay. So let me open it here again. Okay. So for example here. Okay, so if you write it 25, the upper tolerance is 0.2, the lower tolerance, wait. Okay, the upper tolerance is 0.2, the lower tolerance is minus 0.1. So that means if you make some parts in the machine, if you make it, for example, 0.1, 25.1 is still acceptable. Okay, if you make 24.95, yeah, which is less than 25, that is also acceptable. Okay, but however, because of your machinery or because of the method where you're making it, you make it 25.4 millimeters. Okay, it's not acceptable. Okay, so the tolerance or the upper and the lower is actually the maximum, batas bawah, batas atas dan batas bawah. Okay, so the upper level and also the lower level. Okay, is it clear enough? Okay, so for example, let me maybe open, for example, this one, the ATM card. Okay, so the ATM card is maybe roughly around 3 millimeters, right? Maybe, yeah, or maybe 2 millimeters. Okay, so when the manufacturer want to make an ATM card, if they make it 5 millimeters, quite heavy, or make from different plastic, and then it is actually, for example, quite heavy, quite very thick, and then of course it can't enter the machine, right? Okay, so then the tolerance should be maybe 2 millimeters plus 0.02 millimeters, for example. Let me write it here. For example, only 2 millimeters, and then the tolerance may be only 0.1 and also minus 0.1. Okay, so if the there's a manufacturer want to make an ATM card that plastic, and then they make it with different thickness at that time, with, for example, 2.5 millimeters. Of course, it is not on specification. So, and then it can't enter the ATM, right? So the product is off spec. Okay, is that answering your questions? Hello.
Thank you.
Okay. Okay. Anyone? Any other one would like to have a question?
Yes, Miss, I have a question.
Yes, Aska.
For fits, the standard we use, is it ISO or ANSI? Which one is it?
ISO.
Right.
Yeah, we're gonna see it in a second. Yeah. Okay. Any other question, please? So, as a perspective from chemical engineers like me, I know that we can read these in tables, in maps later on, okay? But we also have to know, we have to understand which one that we have to choose, okay? So I think I can, okay, so I can maybe start explain from this one. So the designation size in drawing and machinery, the tolerance principle always determined. So the tolerance in would be always determined. So you can so when it is manufactured in the machinery, it's allowable to happen. Okay, and in for example, and in the drawing, the section doesn't require fit. The tolerance is written as a general whole in the drawing, okay, and then the writing of tolerance on a public note represents the sum tolerance of size of the drawing. I think this one we can explain. We can we can check it one by one, yeah, from the next slides. And general principles: the longer the specimen, the larger the tolerance. If you have piping with maybe 1 millimeters in diameter, the tolerance plus minus 2 or 3 millimeters is fine. Okay, but if you have a very small pipe with pipeline with maybe only 5 centimeter in diameter, the tolerance for that one is very lower. Okay, I think I can explain to you some example, my experience when I did my doctorate degree in Australia. So at that time I have to do experiments on a high temperature experiment. So I have to put samples inside a furnace, and then the furnace is maybe looks like this. It has their built up the built up diameter inside. So it is made by alumina, or look like the ceramic, to heat it up to contain the area inside the furnace. This is called the rotary or the horizontal furnace. And then I have to put some samples inside that, and I have to do a reaction for about 1200 degrees Celsius for a few hours. My dissertation at that time was to produce magnesium metal. So when I purchased this furnace, and then I also have to add another layer or of ceramic. Okay, so I have to make a ceramic. Have to build put a ceramic. We call it like a ceramic like that. So in order this one to be it should be inserted to that one, so I can have a sample of my reactant here. Okay, so because I have to do experiment. Okay, so I know that the diameter of this one is 5 50 millimeters or 5 centimeters. Okay, so it's very at that time I also don't have this knowledge, right, this engineering drawing, because in my curriculum the engineering drawing is not included in the TPB at the time. So okay, so let's buy another, we called it pipe. Yeah, it's like a pipeline, it's like a pipe, but the made from ceramic, because it should be heated in high temperature. And then okay, so I buy that one, and then Australia is such a small country for manufacturing, so not much producer that built something like this, so I have to order it to Germany at that time. Okay, I would like to I would like to order a 46 millimeter alumina tube, I said. Okay, so what happened is when I bought it, it's actually when they make the 46 millimeter, maybe when they manufacturing, there would be like more of that. Maybe they make it 48 or something, or maybe there's some 48 or 49. So apparently, practically, when I buy this one, and then it's cost about $300 per tube, when I put it here, when I insert it here, it's a very hard to be pushed. Yeah, that it can maybe called the fitting, the very tight fit. So also, so I understand. Okay, so when we want to have two parts, which is mating together, then I think I shouldn't choose the 46 one, because there are tolerance, and then maybe the real the real tube that is manufacturing should be more, maybe more than that, because of there is a tolerance. So in their manufacturing, I think that's fine. So so then I have to maybe order the one that is 42. So 42, so the real is actually around 46, so then I have 2 millimeters each side, so they can the alumina can fit together. Okay, so that is the one that I did, for example. Yeah, so, but this actually tell you that when we make things, the the reality always is not similar with the drawing, so that's why we have to check with the deviation. Okay, so this is the tolerance. The tolerance for a general measurement, toleransi umum untuk penunjukan ukuran. So the higher of the nominal size, the allowable tolerance is would be increasing. Okay, this is especially typically for metal, yeah, for I think for ceramic or for other type of compound that should be a different tolerance. So if you make for example the you make a table, okay, the table has length of 2000 millimeters, which is 2 meters. So the nominal size for deviation, if it is a rough deviation, penyimpangan kasar, is about 3 millimeter. Okay, so you can have maybe you can also measure your table right now. Is it maybe the same like it is written in the in the catalog, or maybe slightly larger or slightly lower, because there is a deviation as this one. Okay, but however, when we have a smaller nominal for the measurement, penunjukan ukuran, then the tolerance would be lower as well. Okay, if we only have 3 millimeter specimen, for example, I have this pen, it is only maybe 7 millimeter. Yeah, and also the one that engineer thinks, we also can, which later on you should be able to predict how much is this one, so you can check that with a ruler, what is 10 millimeter for or 1 centimeter, then, and it looks like lower than 1 millimeter, so one centimeter, so maybe it's about 7 millimeter. So if it is around 7 millimeter, so the nominal size that should be required is only plus minus 0.1 millimeter. So the way they manufacturing this one, is from millimeters. Okay, maybe if or maybe 0.8. Okay, so and then again this affect the quality. Okay, so when I bought the iPad, I saw that Apple Pencil is very expensive here, around 2 million or something. So I buy the another one, but yeah, with different type, and then it is like only 500,000. Okay, and then yeah, so and then yeah, so that maybe the tolerance will affect on the quality and also the value, yeah, harga, yeah, the value of that, or the price as well. Okay, and then this one is the tolerance for the radius and a chamfer. Chamfer is the one that if we have like a block like this, and then it becomes like this, jadi ujungnya diperhalus ya, ujungnya jadi rounded, it's called chamfer. Yeah, so it's called chamfer. So for example, we have this one, the end is very sharp, and then we make it rounded like this, it's called chamfer. So again, for the nominal size, there are the nominal that is required. And also this one also about the angle, penunjukan sudut. If we think about a part that has some degree like that, this is all the the tolerance that is required. All right. Okay, so for the number for the the knowledge here, so we have the nominal size, which is the size that is written on the picture, without tolerance, and the tolerance, the difference of deviation from the two sides of limits of nominal, and then we have the upper deviation, so that is the limit of the large size of deviation, and also the difference between the nominal size and the larger or the maximum size allowed, and then lower deviation, the limit or the smallest size of deviation. Okay, this is a very old picture, but I think let me check if I can. So here so the size and tolerance, yeah. So if this one is the hole, and then you put this one is the shaft, okay. So there are some type certain of tolerance. Maybe let me find in some other picture. Okay, so this is the designation of shaft and hole size limits. The first one, if for example, this is the basic size. Okay, so this is the basic size. Okay, yeah, and then so this one is the tolerance, yeah, this one is the tolerance, and this one is the upper deviation as a whole. Okay, and then this one is we call it minimum of size hole. Okay, and this one is the shaft, and the shaft they have the maximum limit of the shaft, and also have the minimum limit of the shaft. So if we, for example, we make a hole very really high with the maximum the size hole, the maximum size of hole, and then we have the shaft only this one, of course it's gonna be very very loose tight, yeah. We have some very quite room over here. Okay, so but however if we make maximum shaft here, maybe it would be a little bit tighter. So the ukuran, yeah, the measurement to know which one is shaft and the right one and which one is the hole tolerance later on would be included in the ISO system. Okay, so okay, so I think the ISO system would be around maybe later on, but before that let me explain to you about the this one, about the size and tolerance. So the real size means that the size obtained from the direct measurement of a finished work piece. Okay, like I said before, after we make the drawing, we're gonna send that to the worker, to the workshop worker, and then they're gonna make it. Okay, and then after that we get the specimen, we will measure it again and then put it as the real size. Okay, so the some of the properties, sifat-sifat, ya, properties that we're looking at first is clearance atau kelonggaran. Okay, so clearance is the difference between the size of the hole and the shaft when the hole is larger than the shaft. Okay, so if the hole is larger than the shaft, that would be the difference between the size of hole and the shaft, and that difference is called clearance. Okay, so kesesuaian longgar or clearance width, that means the hole is much larger compared to the shaft. Okay, so it's divided by the maximum clearance or the difference in the size of the large hole with small shaft on a loose angle, and the minimum clearance, which is the difference of the size in the smallest hole with the largest shaft on the loose angle. Okay, so for example, this one, I think I can watch this one. Yeah, so this one, that is called clearance fit. Why this is called clearance fit? Anyone would like to try? Why this one is called clearance fit or clearance fit? Kesesuaian longgar. This is the hole, the size of the hole, and this one is the shaft. What can you find from this picture? From the diameter of the shaft and the diameter of the hole. Anyone would like to try?
Can I try?
Yes, Aska?
There's still like ample amount of space between the diameter of the shaft and the hole. Like there's space. That's why I think it's called clearance suit.
Yes.
It's not a tight fit.
Yeah,
Essentially.
that's right. So if you look at here, there are some clearance. Yeah, which is, you know, this size is the clearance, right? So because this is the shaft diameter much lower compared to the hole, and then if you look at the video there, they can, you know, quite remove, yeah, you know, remove that one. Okay, they can the shaft is like movable, so and then it is called the clearance suit. Yeah, that's right. Okay, and then okay, so that is the clearance suit. Okay, so yeah, if you look at over here, there are some space over here that it can be a room or the clearance between the shaft and the hole. So the maximum clearance, the difference in the size of the largest hole with the small shaft on the loose angle. So they have a quite loose one. Okay, and then the second type is called the interference. Yeah, in the interference, the difference of the size between the hole and the shaft if the shaft is larger than the hole. And in this tightness, or tightness, kesesuaian sesat, that is the different size of the smallest hole with the largest shaft on the loose angle. Okay, and then the minimal distress is the difference in the size of the largest hole of the smallest shaft on the loose footing. Okay, so here also an example of the clearance fits, yeah, kesesuaian longgar. So you can have some idea here. So this is the length of the hole. So from here to here is the hole. Okay, and over here is the shaft. You can see here that the diameter of the shaft is much smaller compared to the hole, and then so you can just putting this inside, yeah, and then there's still some room over it. Okay, and this is so in a clearance fit, the airspace and clearance exists between shaft and hole as shown in this figure, and these fits give a very loose joints, and then the clearance fit has a positive allowance. For example, there's a minimum clearance between the high limit of the shaft and the low limit of the hole. So this is called a clearance fit or sesuaian longgar.
Just have a question.
Yes.
What's the difference between clearance suit and clearance fit?
Okay. Yeah, I think it is the same, yeah. It is the same. Sorry, I don't. In the slide, why it is repeated again? So this one is basically similar with this one. Okay, so it's about the clearance. Okay, where the hole is much larger compared to the shaft. Okay, can you give me some examples? What is the example of this one? Should be in the. Maybe you can let me open the contekan, ya, the panduan. I also put it in the EduNext about the notes for panduan for this. Give me one second. You can also read it. Okay. Okay. No, they didn't write it here. Okay. I don't know. So I think quite number the example of this one would be somewhere between give me 1 second, I'll need to close the door. Yeah, sometimes it can be happens, yeah, the clearance fit, that one there. Okay, the second one is transition fit. The transition fit, this one has some examples. So it can be push fit, snug fit, ringing fit, where the transition fit, this one, yeah, this is this is in Indonesian, pulpen aliran bawah or aliran atas, yeah, I think, for example. Okay, this is the transition fit. It's a clearance fit or interference fit where the transition fit is actually between the clearance and the interference. So it is quite tight, but we'll still be able to open it and close it. I think a very good example of transition fit is this Lego thing. So it is quite fit. So when we turn it down like this, the part doesn't fall off because there is quite it's quite tight, yeah, but it is easy for them also to open it. Okay, so that is the push fit, yeah, the that one. Okay, the transition fit. I think I think I know one example about clearance fit. For example, about in the bridge, ya, or pagar, ya, ketika kita masukkan the key or the one that goes into your ground. Sometimes the hole is larger, quite larger compared to the snug fit, that one. And that would be an example of the clearance fit. Transition fit would be with overlapping tolerant zone. It is very close, that one. Okay, and the last one is the sesuaian paksa. Yeah. The second one is transition fit, and the third one is sesuaian paksa or interference fit. So which is the shaft is larger compared to the hole. Okay, the shaft larger compared to the hole. For example, paku, yeah, paku and nail and also the wood. So we can push the nail into the wood if we put a force. Okay, we can put a hydraulic force, we can put using hammer something. So this one, yeah, paku or nail is an example. Okay, car wheels, that would be also armature of dynamos as well. So it is a very tight fit and also press fit. Okay, for example, when we fit pipes on in the industrial process, the pipe should be, we have to press it with a hydraulic force. So, and after that we can't open it. Okay, so that's an example of interference fit. Okay, so maybe you can see the difference between clearance fit. This is transition, and also the interference. Okay, so you can look at the over here. So here we still have the clearance with the between the hole and also the shaft, but over here the tolerance is actually overlap, yeah, for the transition fit. And here for the interfit of the shaft is larger than the this one, the hole. So in order to push it here, we need a hydraulic press. We need to put the hydraulic press over here. Oops. Okay, now for the the ISO things, yeah, for that one there. So we actually find there are some types, yeah, there are standards which is called systems. And also there would be a hole-based system or system basis lubang, or the second one is shaft-based system, or sistem berbasis poros. So usually we can I can explain one by one the hole-based system and also the shaft-based system. Okay, so when we have a system based on the hole-based system, we actually determine the hole first, and then we can make the shaft based on that one. Okay, so we determine the hole, and then we can make the shaft, yeah, the is it would be a clearance fit or transition fit or the interference fit. And in the system based on the this one is from the shaft and this is from the hole, we actually make the shaft first and then find the hole. Okay, so here this is still in Indonesian, but that should be fine. So in the hole-based system, all the tolerance is actually determined in the H, yeah, without to calculate the fitting, okay, tanpa mengindahkan tingkatan suaian yang akan dibuat. And then and there are also some codes in it, okay, like large H, and from a smaller one from A to H, and also the transition and the interference. I think it's better if I can explain to you about this one. So this is called the hole-based system. Okay, so in hole-based system we just determine the diameter of the hole. Okay, ukuran nominal dari hole. Okay, so we determine that one, and then we find which type of fit that we're looking at. Okay, do you want to have running fit, which is very, very loose, you know, see, you can see those clearance, or you want to have a close running fit, okay, or you want to have a sliding fit, or maybe you want to have a press fit like this, okay, like light press or press fit. So this tells you which one is, this one would be about the clearance fit, and would be around here would be about the interference fit. Yeah, so in a hole-based system we determine the hole diameter, and then we determine which fit that we're looking at, And then after that we calculate the tolerance for that one, yeah, the tolerance for this one that is required. Okay, so I can read one here. So in a hole basis system, the size of the hole is kept constant and the shaft size are varied to obtain various type of fit. In this system, the lower deviation hole is 0, which is the low limit of hole is actually the same as basic size. The high limit of the hole and the true limits of the size of the shaft then varied to give the desired type of fit. And the hole basis system is commonly used because it is more convenient to make correct holes of fixed size, since the standard deals, tabs, reamers, and branches are not available for producing holes and their size are not adjustable. On the other hand, the size of shaft produced by turning, grinding can be easily varied. So the hole-based system, it is better because we can just determine the hole and after that we can adjust the shaft. Okay, in the previous video, you know how to make the diameter smaller by turning or rotating the specimen. And then with like a sharp blade, they can, you know, lower the diameter of the specimen by using the turning. Okay, it can be easily varied. Okay, so we don't need to change the hole. Okay, so we just need to change the size of the shaft. Okay, so this one, this is the tolerance for the nominal 30 meters to 50 meters. This is the tolerance for the hole, and also this is the for the shaft, and this one is the tolerance for the hole. Okay, so this is quite very bad, but look, like we can see this is a G5 and 6 and so on, yeah, over here, there, and then this one, this is the type of the hole there. Okay, so in now for the shaft based system berbasis poros, so all the tolerance is with we check it, maybe we can look at over here. Okay, this one is the hole based fits here. So all these numbers in the ISO system, this tells you about the type of the tolerance. Okay, is it about the clearance fit or about the transition and about the interference? Okay, and this one is the also you can see the code and then to notify about the clearance fit or interference and so on. Okay, so we can check it from that one. Now the next one, for the shaft basis system, the size of the shaft is kept constant, and then we to determine the different fit that obtained by varying size of hole. So when we do the production, it is a little bit hard to open the hole, yeah. So if the hole is make it larger, then we can't make it smaller again. Okay, so the shaft basis system used when the ground bar or down bar are already available, and this bar doesn't require further machining, and fits are obtained by varying the size of hole. So if we have some bars and the bars is can't be machined again, so the other one, to make the good fit, we have to vary the size of the hole. Okay, in this system, the upper deviation or shaft is 0. For example, the high limit of the shaft is same with the basic size, and the various fits are obtained by varying the low limit of shaft and both limit of the hole. So here, this is the hole-based system. Okay, so in the hole, in the shaft-based system, we have the nominal size of the shaft. Let me write it. So this is the shaft based system. So then we can determine how much is the hole that we have to make in other part based to see this one. Okay, so if we want to have a running fit, that means I have to have a quite large tolerance compared to the nominal size. But if I want to make the a press fit. So that means I need to only make the hole only this length, and after that I will push the specimen of the shaft to the here to the press fit by hydraulic press or something. Okay, this shaft based system is used for some fittings, for example the transportation or the electromotor, mesin derek, ya, mesin tekstil and so on. In the detail, I can't really give you example, but I think if you still curious, you can find the YouTube or something, yeah, to find again about the types of fittings. This one. Okay, and again, there's some numbering for the shaft based system there. Okay, to find which one what this would be correlated to the number of tolerance. Okay, so here this is the the direction for the Swayan or fits. Yeah, so in the hole based system, for example, this is the H7 tells you the nominal for tolerance. Okay, the nominal for the tolerance, and then this would be the tolerance for the shaft. This is the tolerance for the hole. Yeah, so this is tolerance for the hole, and this one the tolerance for the shaft. So so you can find the nominal of this one by looking at the table. All can see there. This one, there's some table about this one. Okay, so through the ISO you can see, okay, for example, I want to have a tolerance is H7. Okay, so first we're gonna see what is the nominal size of your specimen. Okay, my nominal size, my specimen is 50 or 49 millimeters. Okay, so 49 millimeters lies on here. So the allowable one for the hole would be H7 is this one. Okay, so 0 plus 25. Okay, so that is just an example if you want to make a suit or the tolerance between hole and a shaft, and then you can look at that one there. Okay, so I'll go back to here. Okay, so this is a type of an example in pairs between hole base system. So the hole is kept constant, but then you can see here, so if the F7 would be about bearing with noticeable clearance, G6 tells you about bearings that slight clearance, and for example K6 is gear wheels, bushings, and so on. Yeah, of course, maybe most of you doesn't familiar with this one. This should be some in if you like workshop, if you like a bengkel, yeah, maybe you know some of this, but if not, then maybe you just this is the new knowledge for you, yeah, to learn that one. And then here it can be categorized between the clearance fit, transition fit, and also the press fit. Okay, and then this is for the shaft base system. For example, for this shaft tolerance, this one is the for example running fit, sliding fit, ringing fit, or transition fit. Okay, and then to to minimize the cost of production, when we want to know the tolerance, we have to make it as larger as possible with the function. Okay, and then the hole should be lower tolerance, yeah, because a hole is lebih sukar dibuat, yeah, which is rather than shaft. So we need to have a lower tolerance. Okay, so for turning, pengerjaan dengan bubut, we have to get the tolerance with one order better, yeah, what that one. Okay, so this is based on the shaft fit. This you can see all the codes, and this code tells you which one is the clearance fit, traction fit, and the interference fit. Okay, so I think what you need to do, you should be able to select which one the type of suite, and then what is the nominal based on the the requirement that we're looking at. Okay, so this is an example, an ISO symbol in a hole basis or the shaft basis, and tells you which one is the clearance fit, the transition fit, and the interference fit. For example, this one, H11 and C11, is called the loose running fit, which is for commercial tolerance or allowance for external members. This one, free running when the accuracy is essential but it's not good, yeah, okay. Sliding, okay, it isn't run freely but locate accurately. And then with the force, for example, it is suitable for parts that can be highly stressed for string whenever we have heavy dressing forces or required and practical. Okay, so first we have to determine the application, and after that check the pairs between the hole and the shaft. Okay, the hole is the larger, the capital one, and then the next letter is the smaller alphabet. All right, okay, so let's see the next one. So the tolerance for the ISO, here the tolerance is we define it with some alphabets, and the tolerance show the quality of the tolerance and also the measurement of the tolerance, the length of the tolerance there. So the higher the numbers, semakin besar angkanya, maka semakin besar harga toleransinya. Okay, and then for the hole tolerance, toleransi lubang, ditulis dengan huruf besar. So for example, this one. Okay, so here is the 30H7. Okay, so this 30 tells you the nominal. The nominal is 30 millimeter. Okay, the capital tells you about the capital is the lubang huruf besar, ya. So the capital alphabet, that means actually about the tolerance for the hole. Okay, lubang. So this is about the hole. Okay, and then H7 actually the tolerance for hole. Okay, to know which one is the tolerance for the hole, is actually we have to find so we have to find with this one, yeah, H7. For example, H7, so H7, this one, yeah, this is the tolerance for the H7, and we have to look at again also the specimen. Okay, in the specimen we know that it is 30, so at maybe 30 millimeter, so we have to find the tolerance when the nominal is 30. Okay, and this is the nominal when it is 30 over here, so we look at over here to that one and also to that one. So this is actually the tolerance of the hole. Okay, but in it should be divided by 0, 0, 0, yeah, divided by this one, so it should be plus 0, 0.0021, okay, millimeter. So it makes actually the nominal 30 meter plus the maximum tolerance, and the lower tolerance would be 0. Okay, so 30H7 means it have the nominal of 30 millimeter. Okay, that one there, the millimeter, with the maximum tolerance of the upper deviation is 0.0021 millimeter, that one. Okay, and then the lower one is 0. Okay, the number of tolerance may change if we have a change of nominal of the specimen. Yeah, if we have the nominal 40, which is between 30 and 50, then we have to change it, becomes 40. So we're gonna use this line. So then we have to get the tolerance there, that one there. Okay, so the higher the specimen, the longer the specimen, then the the tolerance become different as well, also become larger. Okay, and even in more than 120 millimeters, we have quite large, almost 2 times of the green case. Okay, so again, back to the previous one. So the tolerance for the hole would be, so then is that this one is actually, we can write it as the 30, and then the maximum is plus 0.0021, and the lower one is 0 from the one that I showed you before. Okay, up to here, please. Anyone would like to have any questions? Or let me.
I have
Yeah.
a question.
Yeah. Okay.
Is, is the reading the same for both hole and shaft?
Yes. For
Like the ISO?
Yeah, for the shaft also the same. So for the shaft, this is using a smaller alphabet. Yeah, so if it is smaller alphabet, then it is would be shaft. So here, yeah, this is shaft, yeah, porous. You have the, yeah, you have the small alphabet, but again, you have to find the nominal and then get that one. Okay, so for example, back to here again, let's say you want to have a transition fit. Okay, you have to have transition fit, and it should be locational transition, let's say. Yeah, okay, so that means you have to have the fit, for example, H7 and then K6. Okay, let's say your specimen has a diameter of 50. Okay, so for example, you have 50 millimeter. So you have to define it. So when you make the hole, that would be 50, and then check the tolerance for H7. Okay, check the tolerance for H7, which is the hole. I need to click it right there. Okay, and then if I look at here the H7, and then let's look at on the 50. Yeah, over here, 50 still here. So again, the tolerance, it should be plus 25, and the lower one is 0, right? So I have to, and then it should be here divided by 1000. Yeah, 1000 millimeter. So this actually tells you about the hole would be, the upper one should be plus 0.025, that is the maximum of the hole, while the lower one, the lower tolerance is 0. So you can't make hole lower than 50. Okay, now the next one is the shaft. Okay, so that is the hole. Yeah, the hole should be the lowest the smallest radius would be the smallest diameter should be 50. You can't be lower than that one. Okay, you have to make it bigger with those machine, but the maximum is 50 plus 0.025. That is the hole. Now how about the shaft? The shaft, we looking at the K6, that one. Yeah, so we look at the K6, and then with your ruler here, when you look at here, so the K6 is over here. Sorry. So K6, yeah, that one is the K6, and I'm looking at between 30 to 50 this specimen. So I would like to go that one and go to that one. Okay. So this should be the plus 18 and also plus 2. Okay, so then I can write here back to here. The shaft would be 50 and then plus 0.018 and then plus 0.002. Okay, so if you think about it, between here and here, it's real. This is really small, yeah, because this is plus the difference only 0.00 something, yeah, millimeter on microns. Okay, so it is called it's not very tight, but we call it transition fit. Yeah, so in transition fit is accurate location. So I think the linear tolerance should be very empty space to very lower empty space for them to move around. Okay, so these numbers is actually, I think there should be some it should be included in the exam, where you have to, it can be you convert this type of fitting into here, or when you have this ISO standard ISO here, and then you have to convert it into the number. Okay, Aska, is that answering your question?
Yes, Miss, thank you.
Okay, yeah, hopefully you can have you can do it by yourself. Try to do it again. For example, how about the interference fit and so on, and then you can see here, maybe in the interference fit you will find the shaft is larger than the hole, but that's fine, of course, because in the interference fit that we have the parts which is the shaft is larger than the hole. Okay, so this would be an examples, yeah. So we can see, maybe check one more samples. 40 F7. So for example, 40 F7. So we have to find the nominal 40 around here, and with the tolerance of F7. So F7 is that one there. So it would be here, yeah. So nominal 47, we have the tolerance upper one is minus 0.025 and the lower one minus 0.050. Okay, both of less than 1. Okay, so if we have the hole is 40 H7 and the shaft is 40 F7, we can conclude it is actually very a clearance fit, yeah, Swayam longgar. Okay, see if you have first the hole is H7, which is plus 0.025, lebih besar, ya, for the hole, the lubang, but the shaft is minus 0.05. So it is very, so we have around maybe 0.05 room or clearance between that one. So it can, we can write it that it is a Swayam longgar or clearance fit. Okay, and then let's have a look H7 and F7. So we can have a look to the previous one, H7 and F7. So H7 and F7. Oh, it's not in here. Yeah, it's not typical in here, but I think maybe would be F. There's not F in here. Yeah? There are H8, but it is close to H7. It is called clearance fit, yeah, Swayam longgar, that one. Okay. Okay, another one. So now I'm gonna go back to here, and then please, do you have any other question? Okay, so basically we have later on we have to read which one is the part, yeah, to read this one, and it's based on the nominal size for the, even for the hole and also for the shaft. And then this one also how you write the tolerance in the drawing. Okay, for example, you have a distance between 2 points like this. That is called the diameter 40H7. So that means that this is the diameter, about 40 millimeters, with the tolerance is H7. That is for the hole. Okay. If it looks like this, so that means the diameter is a 40 millimeters with f7, small f, so that would be for the shaft. Okay, so in the drawing, when you just write this one corresponding to ISO system, you send it to the workshop workers there. They can easily make your piece of work. Okay, because we know already the codes. Okay, you can also write like this. Yeah, rather than we put all of the number of the tolerance, we can just write, okay, this is the diameter, and then this is the 30, which is the nominal size, and then the H7, which is the hole, and also the shaft. Okay, so we have to write the tolerance of the hole first, and then after that the shaft. Okay, or maybe we can write it like this, the hole and also the shaft. Or if you want, you can also write again the tolerance, but if it is too heavy, it is also fine to write this one. Okay, and then this tells you about the hole base system, and also the shaft base system. There one. Okay, so this is the maximum and the diameter minimum, and then you can see what is the maximum deviation, yeah, something like that. Okay, so there are types. So if this is the shaft, okay, if this is the shaft for the clearance fit, this would be the tolerance, and this is for the shaft, and this would be the tolerance of the hole, yeah, like we saw it before. So in the clearance fit is quite large, the total tolerance, the length of tolerance between the hole and also the shaft. Okay, and in the interference fit, the allowance is minus, which is the shaft has the tolerance to make it larger or maybe smaller, and also the hole also has the tolerance. Okay, so allowance will always equal smallest hole minus the larger shaft. So that is the the writing there. Okay, so to finish up, let's watch the videos again to hopefully we can continue again the understanding there. Okay, I need to close the stop share and then watch the video again. Where is it? Okay, yeah, so I think we can maybe start from here, yeah. Wait, maybe we can start from here. Okay, so all the coloring, maybe from here. Yeah, so this, for example, this is the diameter for E7. Yeah, this actually tells you the because E, is it a hole or shaft? Because it's capital, so it's a hole, yeah, and E7 is actually, that tells you the tolerance, 0.0 something, 0.0 something. Okay, so let's to sum up, let's watch the video to
uses numbers and letters to convey tolerance zones. Things like M6 and H7. The number, also known as the International Tolerance Grade, roughly indicates how large the tolerance zone is, and the letter indicates roughly where it is. The letter H always means that the specified tolerance zone includes the nominal size as one of the limits, and it diverges into the material. For holes, H means the smallest the hole can be is the nominal size, but it's allowed to be larger. For shafts, H means the largest the shaft can be is the nominal size, and it can only be smaller. The H-tolerant zone is important because it's taken as the middle. Shafts or pins with tolerant zones before H in the alphabet will never be the nominal size. Holes will always be larger and shafts will always be smaller. After H, there are a few tolerant zones, such as J and JS, where the shafts can be larger or smaller, but as you go further through the alphabet, the shafts will get larger and larger, and the whole letter and shafts always get a lowercase letter. Okay, so now we have a naming scheme for tolerant zones. For a given fit, we will usually have one component driving the other one's required tolerant zone. In this example, where we bought the dowel pins, we have no input on their tolerance, so it was a shaft basis fit. If we're designing a shaft that has to fit in a purchased bushing, we can't control the tolerance of the bushing, so we have a hole basis fit. Shaft or hole basis fits often use an H-tolerant zone, respectively, since the H-tolerant zone contains the nominal size as one of the limits. If we're lucky enough to be designing both parts, we do have some discretion, but you would normally base your fit on whatever side of the fit is harder to change. The preference tends to be designing for a hole basis fit, as in general there tend to be more options for precisely reducing the diameter of a shaft than precisely expanding a hole. So what does a fit look like in the ISO system? It's simply the two tolerant zones specified next to each other. An H7G6 fit means, for example, the hole has an H7 tolerance and the shaft has a G6 tolerance. I've cut some holes in this piece of aluminum to show some examples of different fits. This is an undersized H6 tolerance dowel pin. The E7H6 and F7H6 are reasonably loose clearance holes. You can rattle the 12.7mm H6 dowels around a little bit, and they basically drop right through. The H7H6 and G7H6 are much closer fits, and could perhaps be used to locate parts while remaining removable. The JS7H6 is a transition fit that, as you can see, ended up being on the light interference side, but a rubber mallet would work to tap the pin in for a semi-permanent joint. Finally, the P7H7 is an interference fit and would probably require a hydraulic press, or at least a beefy arbor press to install. This might be a good time to point out that, contrary to my labels in my past example, individual holes and shafts can't be called JF7 or H7. The JS7 refers to the tolerant zone that the hole falls in. A hole that is 10.001 millimeters is in the JS7 tolerant zone, but it's also in the H6, H5, and JS5 tolerant zones. You have to remember that we can't measure the hole until after it's cut, and we have to specify the acceptable tolerant zone before it's cut. The fits also have some range to them. For example, these three holes are in the H7 tolerant zone, and these are three H6 dowels. Note how they fall through the holes at different speeds due to the minute differences in the clearance. The numbers themselves are actually determined by the IT system, the International Tolerance System. Every manufacturing process can be statistically analyzed and an IT number can be determined. This means that if I'm reaming a hole, I can look up the reaming process and see that at best I can achieve about an IT7. So I can't specify an H5 or a G5 hole if it's going to be reamed. Likewise, if you have to design something to fit inside a drilled hole, even if you don't have the tolerance for the hole in front of you, you can look up drilling and see that it has at best about IT10. So the whole basis for the fit is going to be around H10. So why would you use this system? Personally, I like how much information is available through just 2 digits. If I have to make a bearing seat on a shaft for an 8mm bearing, I can simply look up what tolerance is required from Machiner's Handbook or something similar. If I need a bearing seat for an 8mm bearing on a shaft that will see reasonably high loads, I can see that it recommends a JS5 fit. The machinists are not going to be happy about that. I know from the fact that it's JS, it'll probably be a transition fit and might need a little force to install, and the 5 tells me I'll need an IT5 process to make it, which will either involve very accurate turning or cylindrical grinding. As another example, if I want a nice sliding fit and the shaft I require will be in the H6 tolerance zone, I can simply specify a G7 on the hole tolerance without having to estimate how much allowance or clearance I want. Specifying a tolerance zone like this on a drawing does mean that the machinist might have to look up the actual numbers, so typically I include the fit as well as the tolerances. So, knowing the different tolerance zones and having a list of a dozen or so preferred fits, we should be able to design parts that fit together how we want. We also have a means of vaguely checking if a manufacturing method will be capable of hitting those tolerances. In addition to the oft-used pin and hole example, the system can be used for internal and external parallel faces, such as keys and keyways, or other features of size. Well, that was a bit of a dry one, but hopefully you found it useful. If you find any mistakes, let me know in the comments so I can correct them. Thanks a lot for watching.
Okay. Okay. So I think the details will also be included in your lab practicum. So have you started your labs?
No, miss, it's delayed
Oh.
until 18th of February.
Oh, really? Oh, okay.
Yeah.
Yeah. All right.
If I
Okay.
remember correctly, I did see like a message about someone getting COVID or something, but I might be wrong, so don't quote me on that. Sorry.
Okay, right. For the solid rock, to be honest, I'm not using that one for my daily activities, but I know. So later on, but my husband using that one for SolidWorks for daily activities as well. So if it is needed, I think in week 7 or week 8, uh, uh, I can ask him to be the guest lecturer maybe to show you using the how to use SolidWorks, yeah, because it is really general engineering or maybe more about mechanical engineering, but at least again for this engineering drawing you will have half of your mark from the written test ujian tengah semester ya, from the, and then half of them also is from your practicum. Okay, I've seen a lot that the students doesn't have the maximum mark, but so I don't want that one. So let's try our best to make sure that we understand the concept, we understand the written test, and also you can also do it well as well in the in the class, also in the lab. Okay, next week we'll continue with geometrical drawing, and I need you some papers and pencils, so we're gonna have a freehand sketching. Okay, so about sketching something, so prepare that one. And okay, I think that's all, and I'll see you again next week. All right, everyone, thank you for listening, and then see you again next week.